afternoon, my YouTube viewers. It is Crystal here, and I'm here to make another video for you about statistics in R. And this particular video is going to be about hypothesis testing as it relates to distributions. So hypothesis testing is a cornerstone of inferential statistics, enabling researchers to draw conclusions about a population based on sample data. At its core, hypothesis testing involves making a claim, a hypothesis, about a population parameter and using statistical techniques to determine whether the evidence supports or contradicts this claim. The process relies heavily on probability distributions, which serve as the foundation for calculating test statistics, critical values, and p-values. And so the last video we talked about the four distributions that are used by R in hypothesis testing. They're the Z, or the normal distribution, the T distribution, the chi-square distribution, and the F distribution. But we're going to talk about that in a little bit more depth in this video. So in order to conduct a hypothesis test, you have to have 4 steps. So the first step is you state the hypothesis. And so basically, when you state the hypothesis, the null hypothesis is generally there's no significant difference between 2 samples or maybe more samples. And the alternate hypothesis is there is a significant difference between 2 or more samples. So that's basically going to be the statement of the hypothesis that you're going to be developing. And then you have to formulate an analysis plan. So you're going to have to decide which probability distribution you're going to use. Like if you want to use a normal distribution, it's going to have to be a large data set. If you want to use a small distribution, if you want to use the T distribution, it's going to be a small data set. And then if you want to compare observed and expected values, it's going to be a chi-square distribution. And then you also have a F distribution that will check values as well. And you can check those values using a box plot. Then you have to analyze the sample data. So you've got to get sample data, and then you've got to analyze it. And so you analyze the sample data by performing a hypothesis test. And it depends upon what type of sample data you have as to what kind of hypothesis test you're going to use. For instance, if it is a large sample, then you're probably going to use a z-test. If it's a small sample, you're probably going to use a t-test. And if you're going to be examining observed versus expected values, then you're going to perform a chi-square test. And they also have the F test that you can use as well that we will be covering in this video. And then what you're going to do is you're going to interpret the results. Okay, generally when you interpret the results, you have to check the p-value. So if the p-value is above the significance level, then you're going to fail to reject the null hypothesis. But if the p-value is below a significance level, then you're going to reject the null hypothesis in favor of the alternate hypothesis. And then you also have your test statistic. So, and then you have to check to see where the test statistic fits in and to determine whether or not you're going to fail to reject the null hypothesis or not. So that's basically, in a nutshell, how you perform a hypothesis test. So the first hypothesis test we're going to use is a z-test. And we're going to perform a z-test using the normal or the Z distribution, because the normal distribution and the Z distribution are the same thing. So if a company wants to test whether the average daily sales exceeds a certain amount, a Z test can be used under the assumption of normality. So we're going to perform a hypothesis test to prove this statement. So the first thing we're going to do is we're going to simulate daily sales. So we want to set our seed, and what happens when you set your seed is every time you run the cell or run the program, the variables are going to be initialized to the same value. So you type in set.seed brackets 1. N is your sample size, which is 60. Mu 0 is your target sales amount, which is 500. Sigma is your standard deviation, which is 40. And your sales is R norm. That's a randomly sampled normal distribution with 60 samples and a mean of 515, a standard deviation of 40. And so that is going to be your sample data. So you can see here that the target sales amount is 500 and your mean is 515. So you can see right here that the mean for the sample is greater than the target mean. So that's going to give you a little bit of information to work on. So we're going to compute our Z test. So X bar becomes the mean of your sales. And so you already know it's going to be around 515 because we've set it to have a mean of 15. And Z, because you know we're using a normal distribution or a Z distribution, becomes X bar minus mu 0. So that's 515 minus 500. So that's going to be about 15, divided by the standard deviation, that's sigma. So that's 40 divided by the square root of n, 60. So 40 divided by the square root of n. So the square root of 60 is going to be less than 8. And so then we're going to say p-val, that's your p-value, is 1 minus p norm of z. And so what this is a one-tailed test. And so you're going to create the p norm that is a probability of the normal distribution of z. And then we're going to print the z and the p-value. And so we come over here to the bottom. So our p-value is, our z is 3.738, and our p-value is 9.26 to the negative fifth. So you can see that your z is 3.738 and your p-value is really low number. And because it's such a low number, it's going to be less than the significance level of 0.05. So what you're going to do is you're going to reject the null hypothesis in favor of the alternate hypothesis because there's evidence that the average daily sales exceed the target. So now we're going to interpret the templates. If p-value is less than 0.05, you're going to print because cat is like a print command. Reject the hypothesis, evidence that average daily sales exceeds the target. Next line. Else, you're going to print fail to reject the null hypothesis, not enough evidence that sales exceed the target. So you can see here that we had a mean of somewhere in the neighborhood of 515 because that's what we set it up for. And it had, so it was 15 points higher than the population hypothesis of 500. So now what we're going to do is we're going to plot our values onto a z distribution or a normal distribution. So we're going to make a curve which is d norm. So we're going to put a density curve on the normal distribution of x. So the normal distribution of x, that's going to be your d norm. From -4 to +4, line width 2, y lab is your label. On your y-axis is density. X lab is your label. On your x-axis it's z. Main is your title, and it says X test is cells greater than target. So what you want to say, determine, is the cells greater than the target? So if the cells is the same as the target, you're going to fail to reject the null hypothesis. And if the cells is greater than the target, then you're going to reject the null hypothesis. And so what we've done is we performed a one-tailed z-test, which is for greater than. And then the critical value is at alpha of 0.05, and alpha is also called your significance level. So Z crit becomes Q norm. So Q is quantile of the norm at 95%. So Q norm, that's your critical, is Q norm at the 95 percentile. And then we're going to shade the rejection region. X shade becomes S sequential. That's going to be a vector that you're creating. Brackets Z crit, that's your critical value, comma 4, comma length equals 200. And Y shade becomes D norm. That's the density of the normal distribution of X shade. And then we're going to put a polygon in there. So we're going to put a vector in there to do it. So polygon, comma C brackets, C crit, comma X shade, comma 4 brackets, comma C, another vector, bracket 0, comma Y shade, comma 0. Color is light coral. Border is not in A or not applicable. And then we're going to add the observed Z statistic. So we're going to add a vertical line. So it's going to be AB line, brackets V, lets you know it's vertical, equals Z. And we've already defined Z earlier in the program. Color equals blue, line width equals 2. And then text, so you're going to put some text into the chart, brackets Z, comma 0.05, comma labels equals paste 0, brackets Z equals round Z to the second place, POS equals 4, color equals blue. We're going to add a critical line. So AB line, brackets V, letting you know it's vertical, equals Z crit, comma, color equals red, LTY equals 2. LTY lets you know that it's a dashed line. We're going to put some text in there, brackets Z crit, comma, 0.1, comma, labels equals paste 0, brackets Z crit equals, and it's Z crit rounded to 2 points, POS equals 4, and color equals red. So you can see here that this is the chart that we have created. It's a z-test with cells are greater than the target. So you can see that we created a normal distribution, a density plot of a normal distribution. And so your z-crit is 1.64 and your z is 3.738. So your z is greater than your z-crit of 1.64. So that means z is not in the normal region of the curve. So you're going to reject the normal hypothesis in favor of the alternate hypothesis to let you know that the average daily sales exceeds the target. So that's the chart that we've made. So the next hypothesis test we're going to use is on a t-test. So a t-distribution is similar to a normal distribution, with the exception that the t-distribution tails are fatter. And a t-distribution is used when you have a small data set, and a normal distribution is used when you have a large data set. So the data set that we're going to be using is going to be a small data set. So we're going to create a t-test with a t-distribution. First thing we want to do is we want to simulate our data, and we're going to set our seed so that every time we run the program, the variables are going to be initialized to the same value. So you type in set.seed brackets 2. So NA equals 12 and NB equals 12. So that's pretty much your number, that your data set. So NA has 12 elements and NB has 12 elements. So you've also got method A and method B. So method A is our norm, and that's a randomly sampled normal distribution of 12 samples, because NA is 12, and the mean is 78. The standard deviation is 8. So that's teaching method A. And then so teaching method B is a randomly sampled normal distribution of 12 samples with a mean of 84 and a standard deviation of B. So you can see that the mean and the standard deviation of A and B are going to be different. And because they're going to be because they're different, it's likely that you're going to reject the null hypothesis in favor of the alternate hypothesis. So the null hypothesis is going to be that the means of the two teaching methods are similar, and the alternate hypothesis means there's going to be a significant difference between the two teaching methods. So we're going to perform an independent two-sample t-test. So t-result equals t.test brackets method A, comma method B, comma var.equal equals false. And so this is going to be a Welsh t-test. So we print off our t-result. So you can see that it's a Welsh two-sample t-test. The data is method A and method B. Your t-statistic is negative 1.8215. Your degree of freedom is 20.314. So your degree of freedom is generally calculated as the number of elements in the data set minus 1. So you had 12 minus 1 is 11. So you would have 11 plus 11 would be 22. But they've calculated it statistically because obviously it was statisticians that wrote this program, and they wrote it for statisticians. So the degree of freedom that they have calculated is 20.314, which is close to 22. Your p-value is 0.08329. So again, what you've got here is the p-value is greater than 0.05. So that means you're going to fail to reject the null hypothesis. You're going to fail to reject the null hypothesis because the p-value is telling you that there is no significant difference between the means of the two samples. You've got a 95% confidence interval of -13 to 0.93, and then you've got sample estimates of mean A is 80 and mean Y is 86, mean B is 86. And so the outcome result is you're going to fail to reject the null hypothesis. No strong evidence of a difference in effectiveness. And so that's what I stated whenever I found out that the p-value was 0.08, so you failed to reject the null hypothesis. So now we've got the interpretation template. So if the t-result $p-value is less than 0.05, you're going to print, because cat is a print statement, reject null hypothesis, evidence that the teaching methods differ in effectiveness. Otherwise, else, you're going to print, fail to reject the null hypothesis, no strong evidence of a difference of effectiveness. So you've got here mean A is 78 and mean B is 84. So I would say 6 points is, to me, 6 points is a bit much, but the way they've calculated it, but you've got your standard deviation is different as well. So the way they calculated it is you're going to fail to reject the null hypothesis. So you can play around with your means and see what happens, your means and your standard deviations, and see what happens. So now what we're going to do is we're going to plot the comparison. So we're going to compute the means and the standard errors. So mean is, you're going to create a vector of the mean of method A and the mean of method B. And then SES, that's your standard error, you're going to create another vector of the standard deviation of method A divided by the square root of the number of elements in A. So that's going to be the square root of 12. So it's going to be a little over 3. And then it's going to be a standard deviation of method B divided by the square root of the number of elements in B. And then we're going to plot it. So plot brackets 1 to 2, comma, means, comma, y lim equals range, brackets 0 minus 2 times SES, and that's your error, comma, means plus 2 times SES. So it's the minus the means minus the errors to the means plus the errors. PCH equals 19, XAXT equals N, XLab is your label on your x-axis, is your teaching method, YLab is the average score, and mean is your title, comparison of two teaching methods, axis, brackets 1, comma, at equals 1 to 2, labels equals a vector you're creating is C, brackets method A, method B, and then we're going to add a 95% confidence interval bars, arrows, brackets 1 to 2, comma, means minus 2 times SEX, comma, 1 to 2, comma, means plus 2 times SEX, comma, angle equals 90, comma, code equals 3, comma, length equals 0.1. And then we're going to add group plots. Points, brackets 1 to 2, comma, means, comma, PCH equals 19, comma, color is going to be another vector of blue and dark green. So we plot it out, and this is what you get. You get the comparison of the two teaching methods. So you have method A and method B. So method A, the mean is going to be slightly more than 80, and method B is going to be slightly more than 85. And so that's what it said, 80 and 86. So it said here, in this particular test, it's saying that there's no significant difference between the two teaching methods, so you're going to fail to reject the null hypothesis. But as far as I'm concerned, I think 6 points is quite a bit. So what I would do, if it were me, I would change the significance level to 0.01. And then if you change the significance level to 0.01 and you ran the test, then it would probably reject the null hypothesis. So it's also, you have to determine what the correct significance level is going to be as well. Because me personally, I think 6 points is a bit much. But it depends on the researcher and what they want. So now we're going to perform a chi-square test. And a chi-square test is when you want to compare the observed values to the expected values. And then so your null hypothesis is going to be there's no significant level between the observed values and the expected values. And a alternate hypothesis is there is a significance between the observed values and the expected values. So we've got a test we're going to perform. As a political analyst might use a chi-square test to determine whether voter preferences in an election match expected proportions. So we're going to create observed and expected counts. So the observed voter counts is observed is a vector of A equals 280, B equals 210, C equals 110. And the expected proportions is going to be a percentage. So expected proportions is going to be a vector of A equals 45%, B equals 35%, and C equals 20%. And then we're going to convert the expected proportions to expected counts. So expected equals sum of observed voter counts times expected proportions. And then what you're going to get is you're going to get the expected counts. So the expected counts are going to be A is 270, B is 210, C is 120. So you can see that that is going to be different from the 280, 210, and 110. So the observed and the expected counts are slightly different. And so we're going to perform a chi-square test. So chi-result becomes chi-square test brackets observed, comma, P equals expected proportions. And then we're going to print our chi-square result. So this is our chi-square result. Chi-square tests for given probabilities. So the data that you're using is observed. So x squared, that's chi-squared, equals 1.2037. That's your test statistic. Degree of freedom equals 2. And the reason why you have a degree of freedom is you've got 3 minus 1 equals 2. So because you've got 3 samples, well, 3 elements in your sample, minus 1 equals 2. Your p-value is 0.547. So basically, since the p-value is greater than the significance level of 0.05, you're going to fail to reject the null hypothesis, and there's no strong evidence of deviation from expected voter probabilities. Okay, so now we're going to interpret the results. So if the chi-square result $ p-value is less than 0.05, we're going to print, because cat is like a print statement that allows you to print text and variables. Reject null hypothesis, evidence that voter preferences do not match expected proportions. Next line. Else, cat, brackets, fail to reject null hypothesis, no strong evidence of deviation from expected voter probabilities. So since the p-value is greater than 0.05, we're going to go with the else. So we're going to fail to reject the null hypothesis with no strong evidence of deviation from expected voter proportions. So we're going to plot observed versus expected counts. and we're going to plot this. And so we're going to combine it into a matrix for plotting. So plot data becomes R bind, brackets observed equals observed, comma expected equals expected, and then we're going to make a bar plot. So bar plot brackets is plot data, comma beside equals true, color is a vector that contains sky blue and orange, main is your title, is observed versus expected, voter preferences. Y-tab is the label on the y-axis, which is number of voters, and legend is true, so that means you get a legend. We're going to add a chi-square statistic to the plot. So we're going to add some text. So in text brackets, paste 0, so that's sort of like a print command. Chi-square equals a rounded chi-square statistic to the 2 points, comma, df equals chi result, $ parameter, comma, and p equals significant brackets chi-square results dot p-value rounded to 3 points, comma, side equals 3, comma, line equals 0.5. So the observed versus the expected voter preferences. So you can see group A, B, and C. So group A is similar, group B is the same, and group C is similar as well. And so this test that we have performed states that there's no significant difference between observed and expected values. So now what we're going to do is we're going to use the F distribution. And on the F distribution, we're going to perform an analysis variance test, which is also called an ANOVA. And the ANOVA allows you to compare more than 2 samples. That's the great thing about the ANOVA. So our test question is, a company testing whether average sales differ across multiple regions would use ANOVA with the F distribution to analyze the data. So we're going to create a hypothesis test to demonstrate this. So the first thing we're going to do is we're going to simulate our sample data. And so we're going to set our seed. So every time you run the program, the variables are going to initialize to the same value. So you set .seed brackets 1, 2, 3. And then we're going to define our region as being a factor. We're going to create another vector, and we're going to repeat repeat A, B, and C 20 times each. And so your cells is going to be a vector with a randomly sampled normal distribution of 30 samples with a mean of 100, standard deviation of 12. So that's region A. Region B and region C are also going to be randomly sampled normal distributions, again with 30 samples. And B is a mean of 110 and a standard deviation of 15. And C is a mean of 105 and standard deviation of 14. So you can see in this example, we have different means ranging from 100 to 110, and we have different standard deviations ranging from 12 to 15. And then so now what we're going to do is we're going to take our data, we're going to take the sales data that we simulated, and we're going to convert it into a data frame. So data becomes data.frame, region, and cells. So you're going to have a data frame that has a region and cells. And we're going to perform a one-way ANOVA on this, and that's an analysis of variance. So ANOVA result becomes AOV brackets cells. It's got a squiggly region, comma, data equals data. And then we're going to print off the summary ANOVA result. Okay, let me see if I can get this. So you've got your summary of your ANOVA result. So in the region, you've got a degree of freedom of 2. The reason why is because you have 3 regions, and you determine your degree of freedom by taking the number of regions minus 1, so that's 2. So your sum of squares is 2640. Your mean of squares is 1319.9. Your F value is 8.9, and your P value is 0.000299. So basically, what that's telling you is your P value is less than the significance level of 0.05. So what that is telling you is that you're going to reject the null hypothesis in favor of the alternate hypothesis, because there is a significant difference between the means of the 3 samples. And then you've got your residuals as well. So your residuals and your degree of freedom is 87, sum of squares is 12,870, and mean of squares is 147.9. So we're going to extract the F statistic and degrees of freedom. So your F value is your summary of ANOVA result 1, and it's your F value 1. So we've already determined that your F value is 8.922. Your DF1, that's your degree freedom 1, is summary brackets ANOVA result, and it's your degree of freedom between groups. And so that's going to be 2. And then your degree of freedom 2 is summary brackets ANOVA result $1 DF2. That's your degree of freedom within groups, and that's going to be 87. And so if we've got, let's see what we've got here. You've got 30 samples. So 30 times 3 is 90. So 30 minus 1 is 29. And 29 times 3 is 87. So that's where you get your 87. And then you have your plot the statistics into a box plot, and we're going to use the same data from the ANOVA example. So box plot bracket cells, squiggly region, comma, color is a vector of sky that we've created of sky blue, light green, and light pink. Main is your title, which is cells by region. X lab is your label on your x-axis, which is region. Y lab is label on your y-axis, which is daily cells, and not equals true. And then we're going to add the group means. So region means becomes T apply bracket cells, comma, region, comma, mean. And you have points, brackets, 1 to 3, comma, region means, comma, PCH equals 19, and color equals blue. And then we're going to put some text in there. So text brackets 1 to 3, comma, region means, comma, labels equals round region means to 1 value, POS equals 3, and color equals blue. So we print off cells by region, and so you can see that we've got 3 regions here. Region A, B, and C. Region A is blue, B is green, C is pink. You've got your means for A is 99.4. Your mean for B is 112.7. And mean for C is 105.3. You can see we've got a box plot. So Q0 is at the very bottom of the chart. Q1 is the bottom of the box. Q3 is the top of the box, and then the little line in the center is Q2. The little line in the center, the second quartile, can be different from the mean. And you can see that because the dot might not be exactly on Q2. And then Q4 is the top of the box plot, which shows you outliers. And so basically our p-value is 0.000299. So that's telling you that the null hypothesis is going to be rejected in favor of the alternate hypothesis because there is a significant difference between the means in the 3 samples. So that concludes the hypothesis test for the 4 distributions that we're going to use in R and in statistics. So we've covered the 4 distributions, being the Z distribution or normal distribution, the T distribution, the chi-square distribution, and the F distribution. And we've covered the 4 tests as well. So you've got the Z test for the Z or normal distribution, you've got the T test for the T distribution, you've got the chi-square test for the chi-square distribution, and you've got the ANOVA for the F distribution. So, because that's what we used in this example, we used an ANOVA, because the ANOVA will allow you to check more than 2 samples. And that's what we're doing in this particular example. So that concludes this video. The next video is going to be on another statistical topic in R. So I hope that you decide to watch it, and I hope you got something out of this video.